Alrighty, section 24.6, our very last one on polarization, which you can think of sunglasses with. So, as you may have seen in the intro video that I posted just before this, polarized electromagnetic waves are ones that are just oscillating in a single direction. So you can imagine a rope or a spring, as was shown in the video, and that's actually a really good analogy. So if the rope is oscillating up and down, then if you have an opening that's vertical, then that wave can pass right through. But if the wave is going up and down, but you're opening side to side, then your wave will not be able to make it through. So we can do this with a rope or with a spring, but it also applies to light or electromagnetic waves. So with polarized light, the electric field fluctuates along a single direction, up and down, and this is our standard picture as we've drawn it. The way that we can depict that, rather than trying to draw this three-dimensional electric and magnetic fields going up and down and in and out, is we just say, hey, look, the electric field is going up and down with the red arrow here. And it has that single direction as the wave moves forward. This is polarized light, which we've assumed up to this point. But natural light, like what comes from the sun, is actually unpolarized. It has random electric field directions, right? So the electric field could be up and down, but it could also be left and right or at other angles. So this is sort of our default light, and we actually have to work to make it more polarized. So if we pass it through a polarizing material like the vertical slit, then it just lets the vertical component of the electric field through. And that means that the intensity is going to drop, right? So the unpolarized light has some initial intensity, S. As it passes through a polarizing material, we now have half the intensity. And you could mathematically show why it's half based on some symmetry, but you could also just take my word for it that if we go from having all directions to just up and down, that's going to be half the intensity. A key detail here is the transmission axis. That's the direction of polarization allowed to pass through. So if you have a vertical transmission axis, then you allow the vertical components of the electric field to pass through. So this is how we can initially polarize the light, but then we get interesting effects if we add a second polarizing material. So the second polarizing material we would call an analyzer, and that's always at some angle relative to the polarized light, and that angle is theta. And so then we have to follow Malaus's law to see how much intensity gets through this second polarizing material, through the analyzer. And so the intensity after the analyzer is equal to the magnitude of the intensity before the analyzer, but after the polarizer, times cosine squared of theta, where theta is the angle from the previous polarizer, from the polarizer and the previous polarization to the new polarization or transmission axis. Now, the key detail here is this equation is just for after the polarizer and then after an additional polarizing material. So if we want to actually analyze light as it comes through, we have to see how it changes with each additional polarizing material. So I added some labels here, right? So if our initial unpolarized light we call S initial, you can call it whatever you like, then we know after we pass through the polarizer, our new intensity is half of what it was before, 1/2 of S initial, and I'm calling that SO because that is what is in Malaus's law here. Then as we pass through another polarizer, as the polarized light goes through a polarized material, then we follow Malaus's law, and that will give us our final intensity. And if we had an additional polarizing material beyond, we could apply Malaus's law again, because it would still be polarized light, it's just in now a new direction that lines up with the transmission axis of the previous polarizing material. So let's try this out in an example. The question here says, what value of theta should be used to the average intensity of the polarized light reaching the photocell is 1/10 the average intensity of the unpolarized light? So there's a lot to sift through here. We want our final intensity that reaches the photocell to be 1/10 the average intensity of the unpolarized light, which is what I called S initial there. So I'm going to switch to the whiteboard so that hopefully you can see me a little better there. All right, so what we have here is we said that we want the final intensity to be 1/10 of S initial. And based on just that, we want to find theta. And so we know a couple of things, right? One, we know our intermediate SO is 1/2 S initial. Whew, sorry, I'm getting really messy over there. Hopefully I'm still on. Not quite. There we go. The other piece that we know is Milhouse's law. S is equal to S naught times cosine squared of theta. So as I set this up, my S here in Milhouse's law is just S final. The SO can also be written in terms of S initial. So I'm going to rewrite Milhouse's law once more. So S is equal to SO cosine squared theta. So my S here is the S final. So that's 1/10 S initial. Sorry for the shadows. And my SO is 1/2 of S initial. So plugging in that relationship as well. And then times cosine squared of theta. So my S initials would just divide out. That will disappear. And we're left with 1/10 is equal to 1/2 cosine squared of theta. And so if we multiply the 2 across, then we'd have 2/10 or 1/5 is equal to cosine squared of theta. The square on the cosine is a little bit annoying, but if we take the square root of both sides, we'll be in really good shape. So now we have cosine of theta is equal to the square root of 1/5. And I'm not going to even worry about trying to calculate that right now. And all I need to get my theta is to take the inverse cosine. So theta is equal to inverse cosine square root of 1/5. Okay, and all of these steps actually are shown within the slides here. So if we go to the next slide, you can see the steps that they've plugged in, and the final angle there is 63.4 degrees. So that's pretty nifty. That was just the only thing they really gave us, is that we wanted our intensity to be 1/10 of what it originally was at the unpolarized light stage. Now, a cool thing is if we go to an angle of 90 degrees, then we have cosine of 90, which is 0, as you may remember. You can check that on your calculator. And that's where no light will get through. The intensity will totally drop. And you can see this with sunglasses, actually. If you have 2 pairs of polarized sunglasses over each other, they just get a little darker, which makes sense. They're both cutting out more of the light. But if you cross them, right, so that one is vertical and the other's horizontal, right, now in between there, no light gets through. And a really cool demonstration of this is actually on the link that I have as extra. It shows how iPads and iPhones are polarized, and that's one of the reasons it can be hard to see the screen if you're wearing fancy sunglasses. So that link is in the materials. This also is how 3D movies work, such as IMAX, is that the projector has two different sources of light, right? One with a horizontal transmission, the other with a vertical transmission. And then those fancy sunglasses that you wear, they have two different polarizations. And so that allows the light to become three-dimensional, right? Where you can have certain colors come forward or off. If you ever take off the sunglasses, you don't really see much effect because it's focusing on only allowing certain polarizations to look different. All right, one last example, this conceptual example. Can a crossed polarizer and analyzer transmit light? So this is supposing a third piece of polarizing material is inserted between the polarizer and the analyzer, right here in the middle. Does light now reach the photocell when A, theta, shown for this middle one, is equal to 0 degrees, is equal to 90 degrees, or is somewhere between 0 and 90 degrees? So let's take a look at this. This is something you can demonstrate if we're in person, right? If you have a polarizer and analyzer, if you don't have this insert in the middle, if that's not there, then no light's going to get through because the polarizer is vertical, analyzer is horizontal, whoosh, all the light is gone. And it'll be much the same if you set theta to 0, right? You send the light through the polarizer, it's all vertical, and then you pass through the insert of a vertical polarizer, and it's still all vertical, and it hits the analyzer, there's nothing that can get through. Similarly, if it's 90 degrees, it's all vertically polarized, and then it hits the 90-degree horizontal, and no light can get through. But a really interesting effect is if it's somewhere between 0 and 90. Because if it's somewhere between 0 and 90, then we notice that the light can be vertically polarized from the polarizer, and it will then become polarized at an angle after passing through the insert. And that angle means that it does have a horizontal component now. And so when it passes through the analyzer, some light can still get through. So this is pretty nifty. Yeah, that you can go from having no light to having some light get through. And then if you go all the way to 90 degrees, no light will get through again. All right, well, that's a pretty good place to wrap up. If you have questions, please do post them in the discussion or bring them to our review session. I'd love to chat more with you. I'll also have office hours, so otherwise, take care, and I'll see you later.